All right, let's get going here. So I sent out, did I send out one review or two? It was just one? Okay. It was an old test or something, right? So make sure you look at that, go through it. And, it's a good guide, but make sure you're also reviewing your homework. And, if you have any questions, you've got until next class to ask. And I think number 7, someone already brought up number 7, so maybe if we have some time at the end, we can take a look at that. But we're going to continue first with what we were doing last time, all right? Let's do that, and then we'll proceed into the review. Just remind me, I'll keep going and going and going. You need to stop me like 10, 15 minutes before class if you want to talk about the test. Okay, so do y'all remember what we were doing? We did Pascal's triangle, exactly. And we had pretty much come up with this idea of a way to get these coefficients using this triangle, right? And then as far as the x's and the y's, I used x and y, right? X and y. It was like the powers, was it x and y or x and h? I did h? Okay. So we had said that, the powers come down on the x's as you move from left to right, and the h's, the powers come up. So if you look back in your notes, we had, what was the last line we had? We did x plus h to what power? Was it 5th or 6th? 5th. And that was x to the 5th plus 5x to the 4th h plus blah, blah, blah. I'm just going to write the one above it. X plus h to the 4th. That was x to the 4th. I don't want to have to redo the whole thing. Plus 4x cubed h plus blah, blah, blah. And one more. X plus h to the 3rd. That was x to the 3rd plus 3x squared h plus blah, blah, blah. Right? That's kind of where we were with this. And we ran out of time, and I said, okay, when we come back, what I want to do is see if we can find a general formula for x plus h to the nth power. Okay, so instead of 3, 4, 5, 6, if I have x plus h to the nth, let's see if we can establish a pattern here, right? So notice that the first term is always going to be x to whatever power is here, right? So what should our first term be? X to the n. Okay? Plus, now look at these coefficients, 5, 4, 3. If you look back in your notes, 2, 1. This number is always also the power, isn't it? So this should be plus n, right? Times x to what power? Yeah, one less than whatever's here. So x to the n take away 1. Right? So whatever that power is, this one is 1 less than it. And then do I have any h's here? Notice in the second term, each one of them picks up an h, doesn't it? So this should also have an h. Plus, now, things are going to get more complicated as we go down here. It's not as easy, but there's some number here in front of the next term. Let's not worry about what it is. But can you tell me the power on x now? N minus 2, right? So it started out as x to the n. The next term would be x to the n take away 1. This would be x to the n take away 2. Do you all understand that? Any questions on that? The power's coming down by 1 each time. And then what about h? How many h's should I have here? 2 factors, right? So h squared. Again, I'm kind of conceding to this. I don't know what this is. I don't care. It's not going to matter to us, okay? And then I keep going, right? Keep going. And it's going to be a bunch of stuff in here, right? Let's not even worry about it. Let's talk about the very last term. What would the very last term be? And I didn't put them over here. But h to the 5th was the last one here. H to the 4th was the last one here. H to the 3rd was the last one there. So this should be h to what? The nth power, the very last one. All right? So the dot, dot, dot just means that there's some pattern just keeps going, you know, and then we get to the very last term. Do you all agree that that's what it should look like? Yes? Okay. Keep that. I'm going to come back to that in a minute, all right? I'm going to need this to do something, all right? Okay, so now, the big idea, okay, of this chapter, and kind of like the beginning of the class, is that if we have a function, I just want to recap real quick. If we have some function f, we can go to some point A on that function. And I referred verbally to this point kind of like, I think I called it the base point maybe once or twice. I think we were talking about can you move from each side, and I said, well, you're going to keep one point the same. So this is your base point. Base point, right? So this is the point we're talking about. And what we can do is we have this new thing called, what is this? What is that? F prime. So that's the derivative of the function at A, right? And what that gives you, what does that give you? When you compute this, what does that give you? It's a derivative, but what does it mean geometrically? It's the slope of the tangent line at that point, right? So if you were to draw a tangent line to this curve, right? That's your tangent line. The slope of that tangent line is exactly what that derivative at A is, right? So this right here gives you a number, right? When you do this computation, it gives you a number, or it gives you a formula. I started to show you at the end of class, like we can do it for specific values of A, but if we do it for general value of A, then we get a formula, right? Yes?
What's your derivative again?
This derivative is, right now, the definition of the derivative is the limit as x approaches A of f of x minus f of A divided by x minus A. That is, up till right now in this class, that is the actual definition of the derivative at A, right? Okay, so that's all stuff we've talked about, right? That shouldn't be like, whoa, what are you talking about? I've never seen this, right? This we've seen. But I want to use slightly different language now. When you talk about a function, if you're looking at it from left to right, like you're reading a book, you think about moving along this function, going up and down, right? Whatever the function's doing. If you're looking at a point and you're finding the slope of the tangent line, what you're doing is you're finding what we call the instantaneous rate of change of the function at that point. You're finding how rapidly the function is going up or how rapidly it's going down at that particular point. Okay, so that's new language. This f prime of A can also be viewed as the instantaneous rate of change of the function f at x equals A. All right, so this is new terminology, instantaneous rate of change. So we have all these things in this class that mean the same thing. Like the slope of the tangent line is also the instantaneous rate of change, but is also the derivative of the function at A, right? So all these things are synonymous, and we need to be comfortable with the language. Questions? Okay, so I'm about to make you upset, all right? And this isn't my fault. This is just, I'm the messenger here again, right? There are two definitions for the derivative of a function. There's two definitions, all right? This is the first one you learn, this limit right here. We have another limit that you have to learn in order for us to proceed in the class, all right? A second definition of the derivative. And you'll see after I do it that sometimes it's better to use that one, and sometimes it's better to use the other one. It just depends. Sometimes the algebra is easier that way than with the new definition, or sometimes the new definition, the algebra is easier there. than over here. And there's nothing that really ever tells you which one to use. You just have to kind of play with them and see, all right? So I'm going to get to this second definition. I'm not just going to put it on the board. I'm going to start from scratch again, kind of the way we built that one, and see if we can build this second definition. So this is the second definition of f prime of a, all right? The second definition. This one is now going to be called the first definition, all right? First definition, now the second one. So I'm going to start with a drawing again. We have some function, right? And we want to know the slope of the tangent line at some point A. So I'm still going to go to some point A. That's still going to be like my base point. And I want to know what the slope of the tangent line is there. So y'all remember when we did this with the first definition, what we did is we took another point over here, didn't we? And then what we did is we connected those two with the straight line, and then we slid that second point over, right? We're going to do this exact same thing, all right? I'm going to pick a second point over here. But in the first definition, we called this point right here x. And then when we called it x, to move it over towards a, we took a limit and we let x go to a, right? So don't write this down, but we put x here, right? And we let that x go to a, and that's what moved the point over, right? We're not going to call it x. We're going to call it this number, wherever we started, plus some amount that we don't know. Call it h. So think about it this way. Like if this was, let's say, the number 2, then maybe this is 2 plus 0.5. See, do you agree that this number plus something should be a little bit to the right of it? And that number h is just going to be arbitrary. So instead of calling this x, I'm calling it a plus h. All right. So let's connect these with the line. Let's connect these with the line, and let's talk about the slope of the line. So if I connect these two together, this will create a secant line, right? We call that a secant line. And what would the slope of this be? We have to figure out what the slope is. So let me remind you, in case it's not obvious, that these points both have ordered pairs, right? So what's the x coordinate of this point? A. What's the y coordinate? So how high is that point? We don't know, right? But it's whatever you get when you plug a into the function. So wouldn't it be f of a? That's this point, yes? And then what about this point? What's the ordered pair here? What's the x coordinate? What's the y coordinate? So what's the x? A plus h, good. What about the y coordinate? Yeah, it's whatever you get when you plug a plus h into the function. So f of a plus h. So we have 2 points, don't we? We have 2 points, and we want to find the slope of the line connecting the two. So what's the slope of a line connecting 2 points? Rise over run. What is that? How do you do that? y2 minus y1 over x2 minus x1, right? It's that formula we've used before. So I'm just going to write it down, okay? This is like my x1, y1. This is like my x2, y2. I'm using the formula y2 minus y1 from college algebra, x2 minus x1, right? Okay, so what's y2? F of a plus h minus what's f of 1, or sorry, y1. F of a all over what's x2, a plus h minus what's I keep on saying f, what's x1, a. Okay, let's clean this up. There's one thing we can do. This is f of a plus h minus f of a all over what happens on the bottom? The a's go away, right? So all you get is h. Does everyone see that calculation right there? If somebody gave me if I gave you a function, right? and I gave you a, and I gave you a plus h, that would give you the slope of the secant line between the 2 points. That's not what we're interested in, right? We're interested in the slope of the tangent line. So how are you going to move this point to this point? Think about, like when this was x, we just said, hey, let x go to a, right? But how are you going to move this over here? Say again? Take away h. Kind of. How about let h get smaller? Let h get smaller and smaller. Think about if this number gets smaller, what happens? Starts moving to the left, right? If h gets bigger, we go this way. But I want h to get smaller. How small? All the way to 0, right? In a limit, though. I want the limit, as the h goes to 0, we'll start to slide this over. So from this, from that, I can right now give you the formula for the slope of the tangent line. It is the limit as h goes to 0, right? That's how I'm going to slide the point. And then it's f of a plus h minus f of a all over h. And that is our second definition of the derivative. See, because the slope of the tangent line, isn't that what f prime of a is? Isn't that what it is? By definition, the derivative at a is the slope of the tangent line at a. And that is the new definition for it. So we now have two definitions. We good? Yes, yes? Let's see it in action, okay? Let's see this formula in a problem. Let's actually do a specific example. So I would commit that to memory. I'm going to put it over here right now. I'm going to put both definitions just so we can reference them. Limit x goes to a, f of x minus f of a all over x minus a. That's the first definition. Then limit h goes to 0, f of a plus h minus f of a all over h. These are your first and second definitions. These are both, right? These are both the derivative of a, right? It's either one, first definition, or you can do the second definition. I always tell my students in Cal 1, I said, do not marry one of those, okay? You're gonna marry both of them, okay? Like, don't commit yourself to just one and say, this is the one I'm gonna use all the time, all right? You are unfaithful to either one of those, understand? Just whatever you need, that's the one you're gonna use. All right, so here's our first example. Let's say we're given the function. I'm going to keep this simple to start. F of x. Let's just do a quadratic. Let's go with something like 3x squared minus 4x. I want us to find f prime of a using both definitions. All right, using both definitions. So let's do the first one, okay? Use the first definition, right? The derivative at a will be limit x approaches a, f of x minus f of a, all over x minus a. That's just the definition, and now I start filling things in. Limit x approaches a. All right, what's f of x for us?
3x squared.
That, right? Okay. 3x squared minus 4x. Now, subtract from that, right? Subtract from that. What?
3a squared plus 4x.
Yeah, f of a, which is what you get when you plug a into the function, which is 3a squared minus 4a, right? But I need to subtract the entire expression, which is going to mean that that negative will distribute. And for those of you who've tried your homework, you've probably seen you have to be real careful with that, because if you mess that up, it's going to be over at that point. The whole goal, okay, let's not lose sight. The whole goal is to get this x minus a to cancel. We know this is 0 over 0. We know it is. We know it is because, I mean, that's why we're here, right? That's why we're doing this. It's because we're trying to get around this tangent line idea where you have a slope at a single point, which was weird. So we have to do a limit. So we know that this is going to go to 0. We want to cancel it. So somehow algebraically, we got to get on the top somewhere an x minus a in parentheses so we can cancel it. So let's go for it. So I'm going to distribute first. We did one like this in class last time. And do y'all remember what it required for us to do this? We had to do what? Yeah, we had to move this, right, this minus 3a squared next to the 3x squared. And then we had to do something like a difference of squares and do some factoring. The factoring was weird, right? Not crazy, but just maybe not as natural as you would want it to be. Okay, so we did, let's see, 3x squared minus 3a squared minus 4x minus 4a, oh, plus 4a. I'm running out of room there. All over x minus a. So what can you do here? Pull out a 3, and then you'll be able to do a difference of squares. And over here, we're going to pull out something as well. I'm going to continue this. So I'm going to pull out a 3 here, get 3, and then x squared minus. Am I going too small with my font here? Can you all see that? I'm trying to squeeze it before this little seam here. Over here, I'm going to pull out, what should I pull out? Negative 4. Let's pull a negative 4 out of these two terms, and we get x minus a. See, the reason we pull a negative 4 out is so we can get an x minus a. All over x minus a. Hey, can we cancel these right now? No. You can only cancel a factor if the factor appears in all of the terms, right? It's not here yet. You need to look at this x squared minus a squared as a difference of squares first. So we continue. Limit. X approaches a. All right, 3, x plus a, x minus a. That's your difference of squares. That's what that is. Minus 4 times x minus a all over x minus a. And now all 3 terms contain an x minus a, right? So you can cancel them. I'm going to cancel them, but I want to make sure all of you understand why you can cancel them. I just want to show you algebraically. What you're really doing is you're saying, look, since this has an x minus a, and this has an x minus a, I can factor it out of the top. And then when I factor it out, what's left is this, 3 times x plus a, and then minus, I pulled it out here, so I have a 4 there. See, that's technically what's happening there. You're pulling the x minus a out, and then over x minus a. And now they're gone. You don't have to do this step, okay? I'm okay on a test if you just cancel them now, but just don't be doing this and canceling here, because then it's wrong, right? All right. Once we're here, we can take the limit. Let's let x go to a now, right? We no longer should have division by 0. So I'm not going to write the limit anymore because I'm letting all my x's become a's. So it's going to be 3. And then that x becomes an a, so a plus a. And then minus 4. A plus a is 2a. And then minus 4. And isn't that just 6a minus 4? Right? So just to kind of recap, the algebra involved here, making sure the negative was here and distributed correctly, rearranging, seeing some sort of weird, almost like a grouping that you're doing here. It's not technically grouping, but it's kind of like grouping. Difference of squares, you have to see that, right? And then you cancel everything, right? That's using the first definition. Let's see what the second definition's algebra looks like. Maybe it's better, maybe it's worse. We're about to find out. So for the second definition, f prime of a now has a new formula. It's the limit. H goes to 0, right? F of a plus h minus f of a all over h. That's our second definition. So be real careful here. The top left corner of this formula says you need to plug what into the function? A plus h. So here's your function, right? Everywhere you see an x, replace it with a plus h. So it's going to look like this. Limit, h goes to 0, 3 times a plus h squared minus 4 times a plus h. And I'm even going to highlight this just so you know what this is. This piece right here is that, right? That's what that is. Now I need to do what? Subtract, right? Subtract. Parentheses. Just I get into a habit of just putting them there because I know I'm going to have to distribute. Now what am I plugging in? Yeah, I'm going to plug a into the function, right? So replace your x's with a's. So it just becomes 3a squared minus 4a, right? So that piece right there, that's our top right piece. So I want to make sure you all see where everything's coming from, right? All of this divided by h. So in the previous definition, what was it we were trying to get to cancel in the previous definition? X minus a. Here, what are we going to be looking to cancel? The h. I just need an h to cancel. So I need to see if I can get an h in all of the terms up there. So look, the good news here is that we're actually not going to do any sort of factoring. All we're going to do is algebra like expansion. We're going to square this, okay? We're going to square it, and we're going to distribute a 3 to it. We're going to distribute the negative 4 through. We're going to distribute a negative through these. Understand? So I'm going to do the squaring over here, even though I shouldn't have to do this, but I will. Everyone here should be pretty comfortable with this. A plus h, I need to square it, right? So that's a plus h times a plus h, and then you FOIL, right? And if you do that, you get a squared plus 2ah plus h squared. Not showing that work. That's what you would get if you put them all together. Trust me? Yes? Okay, that is going to be next to a 3, right? So we still have to distribute a 3 through to all of those. Okay, 3a squared plus 6ah plus 3h squared. Okay, yes? That's that formula over there with a 3 passed through it, right? Yes?
Is it like a general rule of thumb that for the first definition you'll be factoring and the second one you'll just expand?
Not a rule of thumb. I wouldn't say, I mean, because there are some times in this definition where you can factor, and there's others in the other definition where you don't need to factor. So it's not like, okay, if I use definition 2, I get to avoid factoring. All right, so is everyone clear that what's written here is just that right there? Now, what do I still have? Distribute. So what is it? Minus here to here, 4a, right? Minus 4h. Okay, and then here, can't I just distribute that negative through here? So minus 3a squared, and then plus 4a, right? All over h. Okay, if you do things right, good things are about to happen. Do you all see all the good things that are happening? What goes away?
4a.
Okay, 4a, negative 4a, positive 4a. What else? 3a squared minus 3a squared. Those are gone. Anything else? No, right? I don't have anything else that cancels, right? But notice that everything that's left has an h. If you do it right, this is going to happen for you each time, all right? So this is limit, h goes to 0. All right, we have 6ah plus 3h squared minus 4h all over h. And now every term in the numerator has an h, so factor it out. If you want, you can just cancel it right now, but I'm a big fan of, who cares? Just put one more line on your paper. It's not the end of the world here. Pull the h out, right, of the top. Now they're gone. Okay, once we've eliminated that h, now we are ready to take the limit, and you want h to go to 0, right? H to go to 0. So what happens, no more limit, what happens if h goes to 0? Well, that doesn't change, right? 6a is still 6a, there's no h there, so I get 6a. But then plus 3 times h is going to 0, so that's gone, isn't it? 3 times 0 is 0. Then I still have here what? Minus 4. Is that the same answer that we got a minute ago? Yes. Yes?
Will this be on the test?
Today's material will not. I believe last time we did, I did last time ask you for f prime of a. We did do it. So that could be on the test. But I'd only given you one definition.
Okay.
On the test, I don't care if you want to use the second definition, that's okay with me.
Okay.
I'm not forcing you to use the first one. But I could ask you on the test for a derivative using this definition, or using the first one.
Okay.
Yeah. Any other questions? What would you say? Second one, first one? Which one do you like better? You like the second one? I think there's less room for error here. I mean, all you had to do is be able to do that, right? Distribute a 3 through. After that, it was pretty straightforward, all right? Good? Okay, I want to do one that came up. We did this when you came yesterday, right? This problem from the homework. This is a really good problem to show the difference between the two. Yeah, okay, it was, my glasses suck. Here, number 4, what is number 4? There. What is it, x?
Y equals x cubed minus 3x plus 1.
Plus 1, that's it? Okay, thank you.
And the points are 2 and 3.
Okay, once the equation, we're not even going to do that. We're just going to do it in general. So here's a new function. X cubed minus 3x plus 1. We want to find the derivative using both definitions. All right? Now I'm going to kind of, I will say that this one is the preferred one. I mean, as we move forward in calculus, if when you get to Cal 2, if someone were to say, hey, what's the limit definition of the derivative? Most people are going to say this one. They're going to be like, oh yeah, I forgot about that one. But you'll see why in the next section, why that second one becomes kind of the one that we stand by. We just don't want to forget the first one because sometimes it's better, all right? All right, so let's do the first definition. X goes to a. F of x minus f of a.